Chapter 15, we're going to start talking about chemical equilibrium at this point. And I've alluded to it up until this point, but now we're really going to get into it. Okay, so chemical equilibrium. So let's say we have it's a U-shaped tube, and this tube is filled with water. Well, we know that gravity is going to make the level of this water equal on both sides. And that's because it's actually reached an equilibrium. Now, you might think of this as being stagnant, right? That the water molecules are in there, and once it finds its level, the reality is that it's still dynamic. Even though these levels aren't changing, the water molecules didn't come to a complete stop. They're not solid, right? This is a liquid. And so the water molecules are moving back and forth throughout this tube. Now they're moving at the same rate. So the same number of water molecules moving in this direction are also moving in this direction, again, maintaining this level. So this is kind of what our chemical equilibrium is going to be. The only thing is, in the chemical equilibrium, the levels might be here and here, or the levels might be here and here, because it's not governed by gravity, right? So the equilibrium might be uneven between the two. And think about it, if we add more water, right? So let's say we add more water to one side. Well, we know that this thing is going to reestablish equilibrium. This side's going to go down, and this side's going to go up until we reach a new equilibrium. We're going to talk about this in terms of what's called Le Chatelier's principle. So in Le Chatelier's principle, the same thing would be true, right? I can consider this side to be reactants, and I could consider this side to be products. So if I add more reactants, they're going to form products until a new equilibrium is established. If I add products, it's going to go backwards and form new reactants until, again, a new equilibrium is established. Same thing if I would remove. Let's say I would remove products. Well, again, the equilibrium is going to shift from reactants to products until that new equilibrium is reached. Okay? So here's an example. Let's say we have two fish tanks. We have a bunch of brown trout floating around in there, and they are non-social creatures, so they don't school, right? So they're just going to randomly swim around until some equilibrium is reached, till they're just randomly all over the place, and there's our equilibrium. Well, we can express this idea of equilibrium with a new K. Now, this is a capital K, and this is called the equilibrium constant. The equilibrium constant, if we would consider this to be our reactants and this to be our products, the equilibrium constant is just the products divided by the reactants. Now, we're also going to see that it'll be raised, each one of these would be raised to the coefficient in a balanced chemical equation. And we're dealing with overall reactions this time, not elementary steps. Okay? So in this case, there's 5 product fish and there's 5 reactant fish, so that'd be 5 over 5. So this this equilibrium constant would be 1. So when the equilibrium constant is 1, that means we have the same concentration of reactants and products at equilibrium. So basically only half of the reactants formed products. Okay. Now, let's say that we do something and we cause a shift in the equilibrium, right? So we started out with 10, we had 0 on this side, but now we cause something, we do something to cause a shift in equilibrium. Okay, so there it is. And now we have 1 over here who's brave or stupid, and then we have 9 over here now, right? So now we have 1 reactant fish left and 9 product fishes. So again, it's going to be products over reactants, so it's going to be 9 over 1. So now the equilibrium constant is equal to 9. So now you can see that, well, 90% of all of my reactants went to product. So when you have a K greater than 9, that means the products are favored. So at equilibrium, you're going to have more products than reactants. But we're going to see that with our weak electrolytes, remember we said those weak electrolytes only dissociate a tiny bit and mainly remain as a solid. Well, that means that their K value is much less than 1, and that at the end of the equilibrium, there's going to be mainly reactants and only a tiny bit of product. So again, there's our equilibrium constant. So when it is 1, we have equal amounts of reactants and products. When it's greater than 1, we have more products than reactants. We say that the products are favored. And when K is less than 1, barely any products formed. We have mostly reactants, and we say that the reactants are favored. Okay? Any question on what equilibrium constant is talking about, what it means? Okay, let's take an example then. So we're going to talk about the Haber process. This is a very important process. It's where you react nitrogen with hydrogen to produce ammonia. It's actually the number 2 most produced chemical on Earth is ammonia. The number 1 is sulfuric acid, which is used in lead cell batteries. Ammonia is used as a precursor to ammonium nitrate that's used as fertilizer for fields. Okay, so the nitrogen reacts with the hydrogen to form ammonia. And so at first, this is what happens. When there's only nitrogen and hydrogen in a reaction vessel, the only thing that could possibly happen is that it reacts to form ammonia. But as the ammonia builds up in the reaction vessel, it starts to react with itself to go backwards and form hydrogen and nitrogen again. Once the rate of the nitrogen and hydrogen going this way is equal to the rate of the ammonia reacting with itself to go this way, we establish equilibrium between these 3 compounds. Okay, so we could look at it like this, right? So at first, we have no ammonia at all in our reaction vessel, and all we have is 1 mole of nitrogen and 3 moles of hydrogen. As the reaction proceeds, again, we can see that initially it's pretty straight, but then all of a sudden it flattens out. And after a certain point, you'll notice that the number, and we just divide this by a volume, right? And that would give us our concentration. So we can see that the concentrations eventually just reach some steady state. They don't change anymore. Now, again, that doesn't mean that the reaction stops. We say that this is the end of the reaction, but the reality is this is still reacting to form this, and this is still reacting with one another to go back to the original reactants. It's just happening at the same speed. So those are our equilibrium amounts. So we are going to learn how to calculate those equilibrium amounts using the rate constant K, or the equilibrium constant K. And if we look at the rates, so this was the rate for the forward reaction. This was the rate for the reverse reaction. And when both of those rates are the same and don't change anymore, we've reached equilibrium. So that is the definition of equilibrium, when the forward rate equals the reverse rate. Okay, we've seen that in the last chapter. We use this to our advantage to get rid of the reaction intermediates. So if the forward and reverse reaction rates in the system at equilibrium are equal, then it follows that the rate laws are equal, which we've already seen, right? So let's consider the decomposition of dinitrogen tetroxide. And it breaks down into nitrogen dioxide. So again, at first, when you only have the N2O4, it's only going to go to the 2 NO2s. But as this builds up, they're going to start reacting with one another again to go in a reverse reaction to form the N2O4 again. Okay? So we know that again, the rate laws are going to be equal. Okay, so we're going to assume that this is an elementary step in this case. And again, I'll tell you if it's elementary or overall. Okay, so we're going to assume this is an elementary step. And if that's true, then our forward rate okay, our forward rate would be the N2O4 going to 2NO2, and that has a rate constant, we'll call it KF for the forward reaction. And then we have the reverse reaction where the two NO2 are reacting with one another to reform, right? The two NO2 are reacting to reform the N2O4, and that's our reverse reaction, so we'll call that KR. So again, we know that the forward rate constant is equal to the reverse rate constant. Again, we're assuming that these are molecular events, right? These are elementary steps. So the rate equals KF times the concentration of N2O4 for the forward reaction, and rate equals KR times NO2 squared for the reverse reaction. And these two things are related, right? At equilibrium, it looks like that. And if we rearrange it, it looks like this, right? We put the forward over the reverse. Well, that is equal to the equilibrium constant. So in an elementary step or in an overall reaction, all the rate constant expression is, so big K, capital K, equals the concentration of our products, right, raised to whatever power is in that chemical equation. Again, doesn't matter if it's an overall equation, this still works for the equilibrium constant. And then divided by our reactants raised to that power, and that's what we see here, okay? Okay, any questions about that? Okay, now again, remember this is dynamic, so it's happening all the time. It's never stopping. It's just that the rate of this forward reaction is equal to the rate of the reverse reaction. Okay, so again, chemical equilibrium is the state reached by a reaction mixture when the forward rate is equal to the reverse rate. Okay. Okay, let's do a little problem here. So let's say I start off with 1 mole of nitrogen and 3 moles of hydrogen, and they're placed in a reaction vessel at 450 degrees Celsius and 3 atmospheres. Okay, I want to know what is the composition of the mixture if at equilibrium it contains 1 mole of ammonia. So we're going to have to set up what's called an ice table, representing initial, change, and equilibrium. So our initial, we have 1 mole of nitrogen and 3 moles of hydrogen. We would have 0 moles of ammonia, right? We are assuming that we started off with a clean reaction vessel, so there would have been no ammonia in the system, so that would have been 0. Our change, we're going to do our changes in terms of either X, Y, or Z. Generally, we'll use X, but sometimes we need more variables. We got to set up multiple ice tables to solve the problem, okay? So we're going to think about it in terms of X. So we're going to lose, we're always assuming that the reaction's going from reactants to products. So we're always assuming that the reaction's going in the forward direction. We might know for a fact that the reaction's going reverse, but don't worry about that, okay? The math, the signs are going to take care of themselves. We're always going to assume it's going in the forward direction. So that means we're always going to lose our reactants, and we're always going to gain our products. So in terms of X, we're going to lose 1 of these, right? So we'll lose 1X, so minus X. In the case of hydrogen, we're going to lose 3 of them. So it'll be minus 3X. And since we're always going to gain products, we're going to gain 2X of the ammonia. Equilibrium, well, that's just the sum of your initial and change. So this is going to be 1 minus X. This will be 3 minus 3X. And this will be 0 plus 2X, or just 2X. Everybody with me so far? So again, equilibrium is nothing more than the sum of the initial and change. We are going to do ice tables for a long time now. These basic rules never change. Okay. Okay, now we want to know what the concentrations are at equilibrium. Well, we know that at equilibrium, it contains 1 mole of ammonia. So that means 2x must equal 1 mole, right? Because at equilibrium, we have 1 mole. So that means 2x is equal to 1 mole. So just divide through by 2. And that means that x is actually equal to 0.5. Now that we know what x is, we can solve for the equilibrium concentrations of everything else. So if x equals 0.5 at equilibrium, well then 1 minus 0.5 for the nitrogen is just going to be 0.5 moles of nitrogen at equilibrium. And then 3 minus 3 times 0.5, well, that's going to be 1.5 moles of hydrogen. Now, we already knew that the ammonia is 1 mole, right? But we also know that X is 0.5, and it gives you the 1 mole of ammonia. Any questions about that?